A review of what it requires to make causal claims. So the first is there some relationship between the variables? Specifically, this can be measured as a correlation between the variables, and one will often hear this talked about as a covariation between the two variables, or do the two variables covary together? This just means that is there some predictable relationship that ties these two variables together? One of the next requirements for causal claims is whether temporal precedence has been established. And this just means that there is a time order to how these events unfold. And in order to make a causal claim, the cause must come before the effect. You cannot have a system where you make a causal claim except the effect occurs in time before the cause itself. That logically is just not possible. Finally, in order to make causal claims, one must address concerns about internal validity. Remember, internal validity refers to how well alternative explanations have been ruled out. If other explanations have not been ruled out, one is able to say that there is a relationship that is present, but one cannot say that that is a causal relationship because it is currently unknown what other factors might be influencing this relationship. Some terms before we get into the next section. Bivariate designs, this is what we spent all of last lecture talking about. These are designs in which there are only two measured variables, and generally we are establishing a relationship between these two variables. One will hear this a lot coupled with correlations or bivariate correlations, and that just means a correlation between two variables. They are multivariate designs. These are just designs involving more than two measured variables. Finally, longitudinal designs. These are designs that take place over an extended period of time and often have multiple repeated measurements. They can range anywhere from weeks all the way to years. There are some twin studies that have been ongoing for decades. And these types of designs can be bivariate or multivariate. That's just a matter of how many different things will one measure at each time point throughout this long-term study design. Longitudinal designs provide three key pieces of information. First of all, they allow for cross-sectional correlations. What this means is these are correlations that ultimately measure the relationship between the different variables that we are interested in at each particular time point. So for example, if I'm interested in the relationship between exercise levels and eating behavior at 3 different time points over the year, I could calculate what the correlation is between exercise levels and eating behavior at each of those 3 time points. And ultimately what I would have is 3 different correlations, each between exercise and eating behavior, and I could now look at whether those relationships were consistent over time or if they changed over time, and more simply, just whether that relationship is present or not. Next, we have something called autocorrelations. So autocorrelations refer to a correlation a variable has with itself across time. So a way or an example here would be, do rates of exercise at time 1 correlate with exercise rates at time 2, and do they correlate from time 2 to time 3, and so on and so forth. And a way of conceptualizing this is our previous behavior indicative of what our current behavior will be, and is our current behavior indicative of what our future behavior is likely to be? And in many cases, this can provide useful information. Finally, and perhaps one of the most interesting relationships to measure in longitudinal designs are called cross-lag correlations. These are correlations across variables and time points. Specifically, they test if a measure of one variable is related to the later measure of another variable. I will show you a picture on the next slide, which hopefully will make that a little bit more clear. But an example to sort of conceptualize this is, do eating rates at time 1 correlate with exercise rates at time 2, or vice versa? So this is kind of a mixture of the previous two. You are moving across time points and you are moving across variables. So some possible patterns that you could have for cross-lag correlations. One is that both variables are significantly correlated with the other across time points. I will just turn on this pointer. And so what that means is that overvaluation at time 1 predicts narcissism at time 2, overvaluation at time 2 predicts narcissism at time 3, and so on and so forth. And in this case, if both were significantly correlated, then narcissism at time 1 would also predict overvaluation at time 2, and narcissism at time 2 would predict overvaluation at time 3. Just a note about what these are. You can look more in the textbook if you would like more information about this particular study. Here, overvaluation refers to parents overpraising their kids, and narcissism is pretty self-explanatory and refers just to the children's narcissism levels. Another pattern you could see for cross-lag correlations, which is actually what is seen here, is that one variable significantly is correlated with the other across time points, while the vice versa is not true. So here, overvaluation significantly predicts narcissism at each cross time point, while narcissism does not significantly predict overvaluation, and so on and so forth. So when you see this type of pattern, of course, it could be flipped such that narcissism was the significant one and overvaluation was not, regardless. This ultimately indicates the possibility of some kind of temporal order, that it is overvaluation that is predicting future narcissism in each of these cases, but it is not narcissism itself that is predicting overvaluation. And this could lead us to make some type of claim to the effect of, it is the overvaluation of parents that seems to be driving increased levels of narcissism, but not that increased levels of narcissism in children is now somehow making parents overvalue their children. When you see a cross-lag set of correlations in which both directions are significant, it tends to indicate that these variables are ultimately mutually reinforcing, that both of these variables lead to subsequent increases or decreases in the opposing or related variables at the next time point. Your book does mention that there are 3 possible patterns. It does just say that one variable could be correlated in one direction and the other variable could be correlated in the other direction. And it counts those as 2 separate ones. I suppose technically a third could be that there is no relationship whatsoever, but you would probably have been able to establish that in a pilot study where you just measured the 2 items together to see if they had any relationship. When it comes to longitudinal studies and causal claims, such studies allow us to test for relationships. We saw that we can test actually many different forms of correlations, so it allows us to look at sort of nuanced perspectives of the relationships that exist among our variables of interest and how those relationships either change or remain consistent over time. These studies also allow us to establish temporal precedence. Especially based on cross-lag correlations, they allow us to make more grounded inferences about which variables precede other variables and might lead to some type of causal structure. These studies do not, however, allow us to maintain high internal validity. Just because we can measure several variables over time and get a very nuanced picture of how those relationships are changing and moving and interacting, it does not allow us to rule out third variables that could potentially explain the relationship between the variables we are measuring. Okay, if we cannot make causal claims from such a study, why not just shift it over to an experiment so that we could make causal claims? And the reason for that, not in a minute why we can't make causal claims, but why we would want to shift it to an experiment and make causal claims is because causal claims are more newsworthy, more people listen to them, more people believe them, and we just generally like causal claims more than associational ones. There are, however, some difficulties of implementing experiments in certain types of situations. One of those is difficulties with random assignment. Now, it can be difficult to randomly assign cases or participants due to the nature of specific variables that we are interested in. For example, some variables simply do not allow for random assignment because we cannot manipulate them. An example of this would be personality traits. You cannot just randomly make someone into an extrovert or have very low conscientiousness. It's just not something that is possible, and therefore random assignment in those situations is not doable. Often, and we will probably see a little bit of this in the coming lectures, but what often happens in these cases, if you wanted to run an experiment-like situation, you would run what are called quasi-experiments, in which the independent variable is splittable, I suppose is a way to say it, but you do not get to choose how that split occurs, and it is defined by whatever the population is you are measuring. Another hurdle to creating experiments in this form are ethical problems. Sometimes it is just unethical to randomly assign cases to certain levels of a variable of interest. What I mean by levels in this case are just the different variants of a variable of interest you have. For example, in that sense, if I wanted to see the color of a room's impact on people's moods, I could have some yellow rooms and some green rooms and some blue rooms and just measure. In that case, the variable of interest is the color of the room, and the levels are 3 different ones, one being yellow, one being green, one being blue. Okay, back to the ethical problems. Also, just a note, these ethical problems can be exacerbated, especially when there's long-term experiments. So an example to make this clear, if we were interested in understanding the effect of physical punishment on altruistic behaviors, we could not randomly assign children to a physical punishment condition in an ethical fashion. You just cannot say to some people, your kids are going to get beaten for the sake of science and your kids are not. It's just not ethical, and we are prevented from doing so because of the guidelines set forth in the various ethical documents that we all abide by. Okay, some more terms before jumping into the next section. So regression, especially in terms of statistics, right? We're not talking about it in any other forms. It is the process of establishing a linear relationship between two variables. It could be more. We'll talk about that in just a minute. So it differs from correlations in that it provides a specific line function that relates those two variables. Remember, correlation coefficients just establish the direction of a relationship and a standardized magnitude of that relationship. But beyond that, it does not really tell us very much. Whereas regression allows us to make accurate, well, depending on your regression model, allows us to make predictions based on our input information and what we're likely to see in whatever variable of interest we're trying to predict. These lines can be expressed in raw units and standardized units. So standardized units, again, being closer to correlation coefficients. Raw units are units that preserve the original units they came in. Things like dollars or monthly usage of flour in kilograms or so on and so forth. And this line takes the form of y is equal to bx plus a. Many people in algebra see this as y is equal to mx plus b, but in regression, you're going to commonly see it in this form. The reason b is a b is because we call that value a beta, and that's probably why it's a b. And the a in this case stands for an intercept. Now, multiple regression is a form of regression in which you have one outcome variable, one variable that you are trying to predict, and you have two or more predictor variables. Technically, you could have many predictor variables. In this case, k is the number of predictor variables, and, well, like I said, there can be very many of them. And ultimately, this takes a form that is very similar to the line presented in the just single case of regression. And here what you see is y is predicted by the slope times the value of x1 plus the slope of value 2 times the value at x2, so on and so forth through all of the predictor variables plus an intercept of some kind. Now, we're going to sort of go through a soft example to help this make a little bit more sense so that it's not just weird jargony letters that you're supposed to intuit if you've never come across such things before. Oh, I forgot a couple of extra terms. So the criterion variable is the variable that is being predicted in a regression model. This is sometimes called a dependent variable. Personally, I don't like that terminology when it comes to regression models or equations because I think it confuses the idea of a dependent variable with the dependent variable in the experimental method. And this is ultimately just a statistical technique, and it does tend to, I think, using this language bias us towards making causal claims. Because just because we have some predicted variable and some criterion variable does not mean that in real life the actual direction of causality could be reversed, such that even though we are predicting y, whatever y might be, it is actually y in reality that causes x, not the other way around. And the equation will work in both directions. If you learn a little bit about regression and get a sample data set and plug it into a computer, you can run the regression in either direction, using either variable as the predictor and either as the criterion, and it will work in both cases. So regression by itself does not allow you to establish causal structure, which is jumping a little bit ahead, but mainly this is why I don't really like to call the y variable the dependent variable. I think it's better to call it the criterion variable, but ultimately you will hear it called dependent variable quite a bit, and it is up to you ultimately how you're going to think about that. The predictor variable is just the variable that we use to predict the criterion variable. In the equations themselves, these would all be x variables. Okay, now going to the example. So let's say you were interested in predicting a professor's salary, and in order to do so, you had access to two different pieces of information. One, the number of years it's been since they got their PhD, and two, the number of publications they have on their CV. So you stick this information into a computer, you hit the crunch button, whatever that may be, and it provides you with a regression equation. And it looks something like this. So this y hat is just meant to indicate the prediction of the model as opposed to the true y value. And then what we get is 479 times x1 plus 88 times x2 plus 20,138. So in this case, x1 refers to the number of years since their PhD, and x2 refers to the number of publications they have. Okay, one probably wondering about some math teacher who's probably told you once upon a time it's good to learn y is equal to mx plus b, and many of us thought, oh, who will ever use that again? And it's never going to be used in actual life, and well, here you go, it is back. Anyway, here's how you read this equation. So one way to go about it would be, if a professor had just graduated, they had 0 years since their PhD, and they had no publications at this point, we would estimate that their starting salary is going to be $20,138. How are we doing this? Well, I'm just going to turn on this pointer again. Okay, so we have 0 years since they graduated, so I'd plug in a 0 for this x1, and they have no publications, so I would plug in a 0 for this x2, and I would ultimately get 479 times 0 plus 88 times 0, which is altogether 0, plus 20,138, which is the prediction I have. But this is not the only way to read such a regression equation. I could also say that if two professors had the same number of publications but were 2 years apart in their years since their PhD, we would predict that the more senior professor would make an additional $958. So how are we doing this? Well, both of them are starting with this $20,138. We are saying that they have the same number of publications, so they'll both get the same number here, and this number will ultimately resolve to the same number for both professors. So far, this entire term here is the same for both of them. But one professor has a number for x1 that is 2 units higher than the other professor, ultimately leading to an additional income of $958, which we got by multiplying 479 by 2. Now, it might not be 0 and 2 years, it could be 10 and 12 years, in which case if you multiplied 479 by 12 and then also by 10 and found the difference of those two numbers, you would again land on 958. Finally, to look at it from the other direction, you could say that if two professors graduated at the same time, but one had 10 more publications than the other, we could now predict that the professor who had more publications would make an additional $880 compared to the other. And we did this in much the same way, where the 20,000 is constant. Now both of them have worked for the same amount of time, so both of them get the same value for x1, leading this term to be the same for both professors. And this time over here, you have an additional 10 for one over the other, resulting in an additional $880 for that professor. Now, one way that I did not talk about here, well, I suppose it's kind of inherent in this one, but once one has built such an equation, one can take all kinds of different values and plug them in and get estimates of what their salaries are going to be. Ultimately, this is one of the fundamental foundations for all of the prediction algorithms that we use in modern day life. That aside, and we're going to talk about this more on the next slide, this method of statistical analysis allows us to control for other variables. It allows us to say things like, if two people have the same number of publications, what impact does years since their PhD make on their salary? Or if both people have worked the same amount of time, but someone has increased the number of publications they have, what is the benefit of that on their salaries? Okay, a few notes about betas and significance. Whenever people are talking about betas, they're talking about slopes. So in this case, if you were to go back to those equations, they're talking about the b values in front of each of the x's. It is what do I need to multiply my given input variable by so that I can get some kind of linear transformation that results in an accurate prediction about y. You don't really need to understand all the depth of that right now unless you're interested in learning more about it, which I highly recommend. But just note that when people are talking about betas, they're talking about the slope that relates a predictor variable to the criterion variable it is trying to predict. Each beta weight will have a corresponding p-value. Ultimately, this works just like any other kind of significance testing, and it allows us to establish whether our beta weights are significant. What that means is some type of predictor variable a significant predictor of the criterion variable we are interested in? Another way you will often hear about this talked about is if you have a significant beta weight, it means you have a slope that is significantly different than a flat line. There are two types of betas. These betas are interconvertible. So unstandardized betas, these are betas that are in the raw units, and these cannot be directly compared to one another, oftentimes because their units are not the same. You cannot compare sort of number of PhDs with number of publications you have. They are just fundamentally different things. They are, however, standardized betas, and oftentimes these are what are used to make comparisons with other betas. And these have been standardized, meaning that they're no longer in their actual units, but are talking about movements in standard deviations across variables. These can ultimately be compared. Comparison of this also allows you to make determinations of which predictor variables have the most strength in predicting your criterion variable. Or another way you'll hear that spoken about is the larger the standardized beta, the more of the variance it is able to explain in the criterion variable. Finally, betas change based on models, not only the variables. So it is possible that I have some beta weight when I have only two variables. I have some predictor variable and some criterion variable. I plug it into a regression computer or function, it spits out this regression equation, and now I have some beta weight that is ultimately the relationship between these two variables. If I put an additional variable into the model, that beta weight will no longer be the same, because remember, when I have multiple variables in a regression model, I am looking at how a combination of all of them together predicts my ultimate criterion variable, not how each of them individually predicts it. If I wanted to do it individually, I would have to run individual regression models. Once I've run a multivariate regression model, that model is accounting for the relationship of all predictor variables and how together they predict that criterion variable. Therefore, beta weights will not always be constant. They will change depending on how you have constructed this model. Also, I should have said this earlier, but whenever I'm talking about models in this case, I simply mean the line equation. That line equation is a model. It is a representation of a relationship of data that we expect to exist in the world. When it comes to multiple regression and third variable problems, multiple regression allows us to control for the effect of third variables. It can actually control for the effect of many, many variables. And we saw this when we were asking our question about predicting salary based on number of years since a PhD and the number of publications people had. The final two interpretation points of how to read that equation that I gave you were ultimately forms of accounting for some third variable. We were able to see changes in salary when publications were kept constant and all we did is move number of years since your PhD. And we also did the vice versa, where we maintained the number of years since the PhD of the professor as constant, and we changed the number of publications they had to see what impact that had on the final ultimate salary. If we wanted to rule out the potential criticism of a third variable that could be problematic for our claims, we could measure or create a regression model in which we have our primary predictor variable of interest, we have our criterion variable of interest, and now we include this potential third variable that could be problematic as an additional predictor. If it results in a significant beta weight and ultimately is significantly related to our criterion variable, this shows that it is potentially a problematic third variable because it is significantly related to that actual variable we're trying to predict. If, however, we stick it into the model, our primary predictor variable maintains its significant correlation with the criterion variable, and this new variable that was presented as a potential problematic third variable has a non-significant relationship with the criterion variable, we can rule out that this is a variable that could alternatively explain that relationship. Oh, I guess jumped a little bit ahead here, but so we can ask the difference of one variable has on an outcome, for example, in this case, publications on salary, when other variables are held constant, for example, years since PhD, gender, state, age, etc. This does raise this extra point here with the examples I used. A regression does not require all variables to be continuous, which is yet another reason why regression techniques are ultimately so powerful. Mainly we do this with something called dummy coding, and with gender you could just use 2 different numbers or 5 different numbers depending on how you were classifying gender, and you could then ultimately just plug those into a regression model and look at the differences across those as they're interpreted by numbers. It is important to keep track of how you label things because it will spit them back out as numbers, and if you're not diligent in keeping track of what corresponds to what, it could lead to problems in interpretation. Okay, this also we have mentioned a little bit, or I have mentioned a little bit. We can also ask what predictor variables contribute significantly to the prediction of the criterion variable. So put another way, does the primary predictor variable, this is the one we are interested in, still account for a significant portion of the variance? Does it still accurately allow us to contribute to the prediction of this final outcome variable we are interested in predicting? Okay. Regression, as mentioned before, does not establish causation. So when it comes to temporal precedence, such designs cannot always establish temporal precedence, largely because in many times when we measure these things, we measure our various variables that we're interested in all at the same time. And if they're all measured at the same time, it is impossible to know which precedes the other. More than not, this depends on how we measure our variables. So technically it is possible to determine temporal precedence, but that is more a matter of how we set up our measurement, not a product of actual regression, which, like mentioned earlier, is a statistical technique. It is not an experimental design. When it comes to third variables and internal validity, while we can control, and very well can we control for other external variables, there's always the possibility that there is some other problematic third variable, and we're just calling it third variable because that's the name. Technically, this could be the 97th variable you're testing, or you haven't tested yet, but someone presents it to you. But there is always this possibility of some unknown and problematic variable that could explain away your relationship that has not been considered. Remember, it is experimental design, not statistical techniques, that allow for causal claims. So regression by itself is a very, very powerful tool, but does not allow us to make causal claims of any kind. Regressions allow us to make predictions and establish relationships in the form of line functions between multiple variables. Speaking of using these types of association study designs to try and begin to infer cause, we do have a system called patterns and parsimony. So before jumping into what that is, the principle of parsimony is when given two explanations that account for the same amount of variance in some outcome variable, the simpler one is better. So this amount of variance is just if I know some type of measurement, how less uncertain is this other variable I'm interested in? And that's kind of what this meaning of accounting for variance is. But another way of understanding this principle of parsimony, which is oftentimes also called Occam's razor, or I think Sir Henry's canon, is just the idea that when we look out into the world and we think about why something might be the case, and if two different people give us explanations for why that might be the case, and both of those explanations are able to predict these types of occurrences in the future with equal success rates, the simpler of those explanations is the one that we will use and consider to be correct. Now, the idea of patterns and parsimony is the process of investigating causal pathways using multiple correlational or associational studies that all point to a single causal pathway. Now, there will be an example on the next slide, which I hope will make this a little bit more clear. But ultimately, what we're getting at here is there are multiple different studies that are conducted, oftentimes with different questions and different variables involved, but all of them have sort of an overarching theme. And when you have many, many different types of experiments, all conducted in different places with different people and different individuals, but all point to the same sort of underlying mechanism, we can begin to make inferences about cause. So an example here is smoking and lung cancer. And so for a long time, cigarette companies did not want, and I mean, they probably still don't want, to admit that cigarettes cause lung cancer. And they effectively used the third variable problem to stymie scientists and lawmakers alike. This is very similar to what we see in today's world with climate change problems, where even though many scientists come forth and say, there is a high probability that we and our sort of functioning on this planet is a driver of climate change, oftentimes people will come around and be like, well, you can't say that with 100% certainty. And because of how statistics is and how we use it to test our hypotheses, that is always, technically speaking, true. But once the sort of likelihood that it is true reaches a certain threshold, that becomes ultimately a meaningless semantics argument where you are just sort of dividing angels on a pinhead, so to speak. Okay, back to the smoking and lung cancer though. So how did they eventually get the Surgeon General to actually start saying that this is harmful for your health. Because up until this point, there was, and I mean, there still isn't, an ethical way to do an experiment on smokers and non-smokers. You cannot randomly assign a group of 1,000 people to be smokers for the next 15 years and another group of 1,000 people to not be smokers for the next 15 years. You just cannot do that ethically. So, a set of studies were conducted and a pattern was used to establish reasonable cause. And so here, the first of those studies was, the longer a person has smoked cigarettes, the greater their chances of getting cancer. So notice this is again an associational study. They just measured how long people had been smoking cigarettes, and then they measured the number of people out of the entire set who got cancer, and ultimately established proportions and looked then at the correlation between them. Another set of studies involved looking at people who stopped smoking had lower rates of cancer than those who kept smoking. Right? It's similar to the previous one, but has a slightly different take on it. Another that was done was smokers' cancers tend to be in lungs and of a particular type. So this was looking at how the cancers and tumors that smokers have are different than the general cancers that the average population is afflicted with. Another was that smokers who used filtered cigarettes had a somewhat lower rate of cancer than those who used unfiltered cigarettes, meaning that there's something in cigarettes that could potentially be filtered out that could be explaining this different relationship. But I'm jumping ahead of myself there, and you saw that I automatically gave some cause to this, which is something we should all be careful for. But what they found is an association between using filtered cigarettes and lower rates of cancer. Finally, another set of studies looked at how people who live with smokers had higher rates of cancers than people who did not live with smokers. Now, individually, no single one of these studies can establish cause because all of them are associational. But when you begin to put all of them together, one begins to see a pattern. In all of the instances, you seem to have this underlying phenomena of cigarettes leading to some types of lung cancer. And here's where parsimony comes in. I can explain all 5 of these results with the simple causal structure of cigarettes cause cancer. And it becomes much harder now to use third variables, because if you were going to give me a problematic third variable, it would need to be able to explain the results from all 5 of these studies, whereas that is much easier to do with individual ones. So for example, one that got floated was the longer a person has smoked cigarettes, the greater their chances of getting cancer. And one could come around and be like, well, yes, the longer they've smoked cigarettes, sure, but it also probably means the longer they've been drinking coffee, and maybe it's coffee that leads to getting cancer. And it would be, at least statistically, hard to disprove that at its face, but then it would be harder to use that as an example of saying people who stop smoking have lower rates of cancer than those who keep smoking, because if you stop smoking, do you also stop having coffee? And then, of course, another one is, wait, smokers' cancers tend to be in their lungs and of a particular type. So wait, do non-smokers not also drink coffee? And how is that leading to differences in cancers? And then filtered and non-filtered cigarettes, wait, do people who use filtered cigarettes somehow drink less coffee than those who smoke filtered cigarettes? And you see, it becomes very hard to now have a systematic third variable that explains all of these findings, while there is a very simple explanation that is causal in nature that would explain all of these findings. And so this is the idea of using patterns and parsimony in order to start making good inferences about potential causal structures that exist out in the world. This is very common in many of the social sciences that we use today in trying to figure out and understand underlying causes, when it's simply either very difficult or completely unethical to do actual experiments in order to derive cause. Okay, some terms before going into the next section. So mediation, again, something involved in statistics here. So this is the statistical techniques used to test possible mechanisms that underlie an observed relationship between two variables. What that means is if I have seen that there is some relationship between variables, mediation is what allows me to see how that mechanism works. How is it that one variable leads to the other variable? And the basic process of this is testing the change in that relationship between our variables of interest when additional variables are added to this model. Beyond that, you don't really need to know too much about mediation, at least in its mathematical sense, but an overview of sort of the pictograms that I'll show you in the next couple slides, I think helps a lot to sort of the general level of understanding. Okay, so mediators are just variables that help explain the relationships between two other variables. And then there are these variables that are called moderators. And moderators are variables that, depending on their level, they change the relationship between two other variables. So one moderator that gets talked about all the time is culture. You oftentimes find a relationship between variables in one locality, and then you try and move it to another locality, and it does not work. In those situations, culture is a moderator. When you have some relationship that is constant no matter where you go, chances are it does not have a moderating variable. Okay, so how do we look at and evaluate mediation? So I'm just going to turn this on for a second. So this is what the most basic form of a mediation analysis looks like. So we're interested in the amount of deep talk and how it is related to well-being. And one thing we're interested in, or what we're proposing as the means by which the amount of deep talk leads to higher well-being, is that it goes through this quality of social ties. And what we mean by that is, as the amount of deep talk increases, that results in an increased quality of social ties, which in and of itself results in increased well-being. So this would be kind of how to look at and understand this model. Okay, so the first step is testing for the direct relationship. Is the amount of deep talk actually related to well-being? If it is not, there is no need to do any kind of mediation because there is no relationship. If, however, we have a significant relationship here, we can move on to the next step. This would be testing the relationship between our predictor variable and our mediator variable. So is there a relationship between the amount of deep talk and the quality of social ties? If this relationship does not exist, well then the quality of social ties cannot be a mediator because it is unrelated to our actual predictor variable. Next, we would test for the relationship between our mediator variable and our criterion variable. Same type of logic here, that if this potential mediator is not at all related to our criterion variable, it cannot be a mediator. It is just simply something related to our original predictor variable. Finally, in order to actually test the mediation itself, we would run two different regression models. The first would be just the amount of deep talk relating to well-being, and we would look at this relationship, the strength of relationship C. Then we would run another regression model in which we would add the quality of social ties. And you can stop for a second here and think about, what does it actually mean for that mediation to be true? I'll give you a second to pause there. Okay. What we would hope to find if there was an actual mediator is that once this relationship has been added to the model, this relationship will go down. And in fact, it might even become non-significant. And now what we would be doing with this is saying that ultimately it's not deep talk that is directly related to well-being, but the relationship between them is actually working through the quality of social ties. And this is ultimately how we establish whether mediation is there or not. And we will compare C to what is oftentimes called C prime. C prime is this relationship when this model is being taken into account. And there is something called a Sobel's test that allows you to compare these two. And that too gives you a p-value that allows some proportion value of what the likelihood of this mediation being the case or not is. Finally, and perhaps one of the most important and most misunderstood things about mediation is that temporal order is very important. You cannot have a mediation analysis that has incorrect temporal order because ultimately mediation analyses are done on potential causal pathways. What this means is the predictor variable must come before in time, then the mediator variable, which also comes before the final criterion variable. Because think of the logic of what we're saying. We're saying amount of deep talk is related to well-being through social ties. It's as I have more deep talk, my social ties get better, which leads me to have more well-being. I can't have amount of deep talk and social ties exist in the same, because then there's not a temporal sequence. If these two exist at the same time point, then I just have two predictors that happen to be correlated, both relating to well-being. But I can no longer talk about how that relationship is actually working because I no longer have the correct time sequence. If you go through a lot of the literature, you will find that there are so many mediation analyses that have been conducted without any care whatsoever to this temporal precedence. And I cannot stress this enough. It is incorrect methodologically to do mediation analyses in that form. Now, a computer is going to spit out the responses no matter what. Like I said about the regression, technically you would give the computer an outcome variable that was measured 10 years before both of these, and it will give you a result. Whether that's significant or not is immaterial. It will still give you a result. Only you or the experimenters can know if that sequence is correct by looking at the methodology involved in generating that data. If it is not, you cannot run a mediation analysis. If you'd like to know more about this, Dr. Tate is a great person to ask, and she has in fact written papers on this very subject. Okay, let's talk a little bit about mediation, moderation, and third variable problems. So this first column here is related to mediation. This is what we've been talking about. So the definition or a question asking related to mediation would be, why are two variables related, right? How can we explain their relationship? So in pictograms, it's just, okay, I have A and B are related, but I want to know why they're related. And I propose that they're related through C, such that A leads to C, which in turn leads to B, and that's why these two variables appear to be related. So a real-life example of this would be, it has been fairly reliably shown that viewing violent TV is associated with increased levels of aggressive behavior. And a potential mediation model explaining this relationship could be that viewing violent television leads to one becoming desensitized to violence, which in turn leads to greater aggressive behavior. This would be an example of mediation. Now, moderation is, remember, a variable whose levels at different states lead to different relationships observed between the variables of interest. So a way of asking this would be, are certain groups or situations for which two variables are more strongly related? So A and B are related, but for only some types of C. And so this could be different countries, this could be different genders, this could be different socioeconomic statuses, this could be different times of day, it doesn't really matter. This is just saying that at type 1 of C, there's a small relationship between A and B, and at type 2 of C, there is a very large relationship between A and B. Sometimes you'll even see relationships disappear entirely or move in opposite directions. So here would be a relationship between viewing violent television and aggressive behavior, and here you can see that when parents discuss TV content with their children, there is a relatively small relationship between viewing violent television and aggressive behavior, while when there is no parental discussion, there is a much stronger relationship between viewing violent television and aggressive behavior. So here we're just looking at how this relationship changes depending on different classes in which that relationship could exist. Finally, there's the third variable problem or extraneous variable problem, and this is just that two variables are correlated, but only because they're both linked by some unrelated third variable. And so there's again a relationship between A and B, but that's only because A is related to C and B is related to C, and because both of them are related to C, it appears as if A and B are related. And so an example of this would be, again, the relationship between viewing violent television and aggressive behavior exists, but that relationship only exists or appears to exist because having lenient parents allows you to do more of both. Also, you can find this in your textbook if you would like to spend some more time looking at it. I would definitely at least become comfortable with the difference between mediation and moderation, because this is something that trips up a lot of people. Okay, finally we get to multivariate designs and validity. So we will and are rightfully able to talk about construct validity in multivariate designs. These are just things about how well were the variables measured, were the measurements reliable, were measures previously validated. So this is all about how well do the items we use to measure our various components actually relate to the components or ideas we are trying to measure. We can examine external validity, and this is just relating to how well does the information from our study and models generalize to other samples or even the population at large. And remember, we do this primarily through analyzing how our data was gathered. Was it gathered in a randomized fashion, or were there systematic biases in how that data was collected? Another way of that randomness being talked about is, did all people I'm interested in potentially making claims about have an equal chance of being in my study or not? Finally, there are concerns about statistical validity, and this is often done through examining what the effect sizes were, what relationships were significant or not, what were the sample sizes used, and was exploratory data analysis conducted. And that just means, were there outliers in the data? Please remember that because regression is also about looking at linear relationships, it is susceptible to the presence of outliers. And by that same token, curvilinear associations can cause problems for regression because most forms of regression are about linear relationships. I did say most forms, and that is because, just like I said, you can put categorical relation or variables into a regression model. There are actually regression models to study curvilinear or even higher order relationships.